Example problem 3 reads, calculate the decrease in temperature when 2 liters of gas at 21 degrees Celsius is compressed to 1 liter. So the word compressed is going to be key here to figuring out which equation you're using. So an example of a compressed gas is a tank of oxygen that a patient would be using to inhale if they're low on oxygen. So compressed means that gas particles, which are normally very spaced out, think about the air just in a random room, very spaced out, are shrunk down to where they're very close together. So that's going to increase the pressure and it's going to decrease the volume, which is exactly what we saw in the previous problem with Boyle's law. So the word compressed means that conditions have changed. Pressure was increased where the volume was decreased. So that means since conditions have changed, you're going to be using the combined gas law equation, which is P1 V1 over T1 equals P2 V2 over T2. So rereading the problem, liters is a unit of volume, so we know we're going to have a V1. Celsius is a unit of temperature, so we know we're going to have a T1 of 21 degrees Celsius, which means we're going to have a set of V2s and T2s. It's asking us to calculate the decrease in temperature, so it's pretty straightforward that we're going to be looking for the temperature, and it tells us that it was compressed to 1 liter. So the one variable in the combined gas law equation that was not in this problem was pressure. And so pressure cancels and you're left with an equation that is V1 over T1 equals V2 over T2, which is exactly what Charles's law is in the previous slide. So doing a unit check here, volume is in its correct units, which is liters. However, temperature is not. It's in units of degrees Celsius, and we need to go to units of Kelvin. So the formula to convert from Celsius to Kelvin is temperature in Kelvin equals temperature in Celsius plus 273.15. So that's going to be 21 degrees Celsius plus 273.15, which ultimately is going to equal 21 plus 273.15, 294.15 Kelvin. We don't say degrees Kelvin, we just say Kelvin. So plugging these variables into our equation, V1 is 2 liters. Our new T1 that we calculated is 294.15 Kelvin equals V2, which is 1 liter, divided by X, or T2. So you can either cross multiply, or for me it's easier to just handle one side and then handle the other. So 2 divided by 294.15 is 0.00679, so 0.0068 liter kelvins, because that didn't go anywhere. Nothing canceled here. Equals 1 liter divided by X. So remember the trick to rearranging everything correctly when you're looking for X in the denominator is to change places with what's on the other side of the equal sign. So our final equation to solve for X is going to be X equals 1 liter divided by 0.0068 liter kelvins. So you can see where liters cancel when we're left in Kelvin, which is appropriate for temperature. So in your calculator, 1 divided by 0.0068 equals a final T2 of 147.058, so 06 Kelvin. Let me know if you have any questions about example problem 3.